Today we're going to be looking at magnetism. Well, what exactly is a magnet? A magnet really is just an object that exerts an attractive force on magnetic materials, namely iron, nickel, and cobalt. Those are the main three materials. So if I have let's represent it with a rectangle here. If I have a magnet, by definition, it should attract each of these, materials made out of each of these three elements. But looking deeper, these forces of attraction can also become forces of repulsion. When two magnets are in the same vicinity as each other, and they have magnets usually, in real life they only exist in two dipole states, meaning that they have two poles. When two of the same poles, like poles, are next to each other, this will cause a repulsive force between each magnet, pushing them further apart. Whereas if they were together and they were of opposite poles, that would push them together, an attractive force. But let's look at the mechanism behind how these forces are exerted, that being magnetic field lines. Simply put, magnetic field lines show where the north pole of a compass would point to and act towards if it was in the magnetic field. So for this bar magnet, the magnetic field lines would be as the following, and more of them being close together, greater magnetic field line density basically means your magnetic field, represented with the letter B, will be stronger and higher. Looking at some equations now, it's also important to know that for a moving charge in a magnetic field, it can deflect it accordingly, and we can find the force that acts upon it. So for example, say we have magnetic field lines and we have a beta particle over here. Its direction of travel is 60 degrees to the direction of the magnetic field lines. Its velocity is 1 times 10 to the 6 meters per second. Its charge of an electron we know is 1.602 times 10 to the minus 19 coulombs. And the angle we know is 60 degrees. The equation in question is F equals BQ V sine theta, and this will essentially tell us the force experienced by the beta particle of the charge in a magnetic field. Let's solve for F. You can pause the video now and go ahead. Okay, looking at the equation, it just seems we need to substitute the numbers in. This magnetic field B, I forgot to say, it was recorded to be 0.5 milliteslas. Now you can go ahead and solve the question. Be careful of the unit conversion though. 0.5 times 10 to the minus 3 times the charge times 10 to the 6th the velocity times sine of 60 is essentially going to give us our result. And that being, let me make some space, F was then calculated to be 6.94 times 10 to the minus 17 newtons. But say I want to find the maximum force that the charge can experience Well, in this case, that moving charge, our beta particle, will have to move perpendicular to the magnetic field lines. And looking back at the equation, the only way to make sure that F is a maximum is that sine theta has to be equal to 1, because that can range from -1 to 0 to 1 if we remember the graph for sine theta. So we know that sine theta has to equal 1 for F to be a maximum. So plugging all the numbers back in, we essentially just have F equals BQV, given that sine theta is now just going to be 1. So solving for F, we'll get a value of 8.01 times 10 to the minus 17 newtons. As you can see, that makes sense because our value is indeed larger than the original value when the beta particle was entering at an angle of 60 degrees. So that's essentially the basics of magnetism, specifically on the force experienced by a moving charge in a magnetic field. Thank you for watching the video. Please give a like and subscribe.